Hello everyone, and I'd like to announce that today is actually my birthday and we're going to celebrate that with doing a bunch of these crazy integrals. Anyway, let's get going on the first one because we got a lot to do today, so I don't want to waste any time. This is the integral going from 0 to pi of the integral going from 0 to pi over 2 times x of another integral going from negative y to positive y, and then we have x times the cosine of z over y dz dy dx here. And how we're going to start with this, you notice this x here. The x, when there's a dz, is just a constant. When there's a dy, is also a constant. We move that out all the way to here. And next, what we're going to do, we're going to realize that y in dz is a constant. 1 over y is also a constant, by that matter. And we can, when we integrate this, you divide by 1 over y. So you multiply by y. And then this cosine becomes a sine, and then this z becomes just itself. So it's a lot of stuff to do, but I'll show you every step. So first step, move the x out. Then we're going from 0 to pi over 2 times x times the integral going from negative y to y of cosine of z over y dz dy dx. And then, what happens if we integrate cosine of z over y, when y is just a constant? Well, we get y sine of z over y, and then we just plug in the numbers. So, let's see, we have here the integral going from 0 to pi of x times the integral going from 0 to pi over 2 times x. And then right here we have, let's see here, this is, once again, when you integrate cosine of z over y, you divide by that 1 over y, which is just y. And then we have this turned into a sine. And then this z over y is still the z over y. And then we can just integrate that like that and then plug in numbers negative y to positive y, dy dx. And then, if you notice here, if you plug in positive y to here, if you plug in positive y to z, then y over y is just 1. So we have y times sine of 1. But then you're going to subtract y times sine of negative 1. Plug in negative y to here, we get negative 1. But sine is an odd function, meaning that sine of negative x is actually equal to negative the sine of positive x. So at the end, we just get y times sine of 1 plus y times sine of 1, which is 2 sine of 1 times y. And then you could just move that outside. So what we have here is, if I plug in these numbers, we get the integral going from 0 to pi of x times the integral going from 0 to pi over 2 times x of, let's see here, this is going to be y sine of 1, and then you're going to subtract. Once again, sine is an odd function, so this becomes a plus. And then we have y times the sine of 1, of course. And then dy dx, of course. And then this 2 times sine of 1, that's just a constant. We move that out. And then we're just going to integrate y. That's 1/2 y squared. So we have this equals to 2 times the sine of 1 of times the integral going from 0 to pi of x times 1/2 y squared, and then we go from 1/2 y squared, and then we go from 0 to pi over 2 times x dx right here. And then we're going to move all the way to the top again because we're going to do just a little bit of moving things around. So first of all, we can cancel this 1/2 with this 2. So we get this is equal to the sine of 1 times the integral going from 0 to pi of x. Plug in 0, that just goes away because, well, 0 squared is 0, and then subtracting 0 is still 0. We have pi over 2 times x squared. So we have, let's see here, pi squared, and then we have an x squared, and then you divide by 2 squared, which is 4. Dx right here. And then after that, we just move these constants out, and then this becomes x cubed, and we will integrate that. We will get 1/4 x to the 4th power. We get this equals 2. Alright, so we have pi squared over 4 times the sine of 1, and then we have the integral going from 0 to pi of x cubed dx, of course, and then we're going to integrate this, so we have pi squared sine of 1 over 4 times, let's see here, integrating x cubed, we get 1/4 times x to the 4th, and then we're going to go from 0 to pi, of course, and then this 1/4 and this 1/4 make 1/16. Pi to the 4th times pi squared is pi to the 6th. We will get this equals to pi to the 6th sine of 1 over 16. That is the answer to this first integral, of course, and then I'm going to step aside. Alright, hopefully you got a chance to see this integral. It's the first integral of 5 that we're going to do. And just erasing the board real quick. I haven't actually done 5 integrals in a row, so I might mess up here or there, but hopefully I won't. Next, we have this one. The integral going from 0 to 2 pi of 1/x squared times the integral going from 0 to x of the square root of y plus 2x dy dx. Firstly, you will notice that when you're integrating with respect to y, this y plus 2x, you can do a substitution, let u equal y plus 2x, and then the 2x here, if you're differentiating with respect to y, that will go to 0. So, let me start with the u substitution, like I said. Let u equals to this y plus 2x. Then we have du equals to dy, because x is just a constant when you're integrating with respect to y. And then we could just plug in the numbers here. So we have, as y equals to 0, u would be, plug in 0 to here, we get 2x. Y equals to x, u would be, plug in x to here, we get 3x, of course. And then we're going to have to plug these numbers and this new variable into the interval. So we have this equals to the integral going from 0 to 2 pi of 1/x squared times the integral going from 2x to 3x of the square root of u du dx, of course. And then we have the square root of u. Think of that as u to the 1/2 power. Add 1 to the power, divide by the new power, and then we would get 2/3 u times the square root of u, and then we just plug in numbers. So, this is going to be a lot of algebraic work after we finish the integral. So I have 1/x squared, and I'm going to do this in my head here. Plug in 2x, we get, well, first of all, plug in 2x, we have 2/3 times 2x times the square root of 2x. And then, of course, we have, no. You plug in 3x first, sorry. So plug in 3x, we get this, and then we're going to subtract, plug in 2x, we get 2/3 times 2x times the square root of 2x. And then all integrated with respect to x, of course. Next, we have some cancellations, of course. So we have this 3/3, they cancel. And then we're going to distribute this 1/x squared out. And then, well, first of all, I'm going to do that. And then I'm going to do further simplification. So, the integral going from 0 to 2 pi of. Since these are canceled, we get 2. But then this x squared and this x will cancel into just 1/x. And then you multiply by the square root of x, we get 1 over the square root of x. And then we have this extra square root of 3. Like that. And then you're going to subtract, first of all, dx here. And then you're going to subtract the integral going from 0 to 2 pi. Okay, let's see here. 2 times 2x is 4 over 3 times x. But then you have to divide by this 1 over x squared, right? And then you have to multiply by the square root of x. So we also get 1 over the square root of x. I hope that makes sense. And then we have this square root of 2 left over like that. And then put a dx right here. Alright, and then we could just go to all the way to the top again. Alright, so move all the constants to the front. We get 2 square root of 3. The integral going from 0 to 2 pi of x to the negative 1 over 2 power. And then it's dx, and then you're going to subtract 4 over 3 times root 2. We get 4 root 2 over 3 times the integral going from 0 to 2 pi of also x to the negative 1 over 2 power, and then dx like that. Let's see here. Integrate these is easy enough. So we have this equals to 2 the square root of 3 times, this is 1 over 2 times the square root of x, and then we go from 0 to 2 pi. And then we're going to subtract the 4 root 2 over 3, and then this is also 1 over 2 root x, right? You can just do this using your old methods of integrating polynomials from 0 to 2 pi, of course. Actually, this is not a polynomial. This is not a polynomial because you have fractional powers, but x to some power should be better. Anyways. Okay. What do we have next? Well, if you plug in 0 to here and here, well, first of all, I copied the entire problem wrong. I am really sorry about that. These are all ones, first of all. I just realized that. Okay, great. I'm gonna have to erase all of these. Oh, God. I copied the question wrong. That was what happened. That's great. I'm not proud of that. Anyways. Plugging in 1, we just get 1/2. And then plugging into pi, we get 2 root 2 pi. Of course. And then, so yeah, this equals to 2 times the square root of 3. 1 over 2 root 2 pi minus plug in 1. We will get minus 1 over 2. We don't take the reciprocal. We do not take the reciprocal. Okay. Alright, so this is going to be oh my God, 2 root 2 pi minus, this is just 2, and then you're going to subtract 4 root 2 over 3, 2 root 2 pi minus, and then plugging in 1, we get 1. Okay, actually, no, we get 2. We get 2. Okay, so let's see here. We have this 2, actually, you know what, let's factor out a 2 while we're at it. So we have, this is 4 root 3, this is square root of 2 pi minus 1, and then you're going to subtract, this is going to be 8 root 2 over 3 times the square root of 2, the square root 2 pi minus 1. I hope you guys can see that. We have a lot of algebra going on. And then we're going to factor out this square root of 2 pi minus 1 out. We get this equals to the square root of 2 pi minus 1. And then you're going to multiply by 4 root 3 minus 8 root 2 over 3. I think that is the answer. I am mostly sure that is the answer. Anyway, take a look at that. And then we're going to move on to the third one, which I'm going to tell you needs power series. Actually, you actually need pretty simple power series, but you also have to do limits, L'Hopital's rule. I've never said that word in my life before, so bear with me. Anyway, great. Okay, I'm trying not to erase my equations. Alright, like that. Okay, next we have the integral going from 0 to 1. That's a little bit small, I think. The integral going from 0 to 1 of x times the natural log of x over 1 minus x squared. Before this, I have to say something. I doubt I can fit this entire thing into one board, so I'm going to try my best here. First off, we're going to look at this 1 over 1 minus x squared. Well, think back to how 1 over 1 minus x equals to the sum n equals to 0 to infinity of x to the n. Next, plug in x squared to that, so we get 1 over 1 minus x squared. On this side, you would basically multiply the powers to get x to the 2n. And then we're just going to plug that in right there. So, we get this equals to, going from 0 to 1 of x times the natural log of x times the sum. N equals to 0 to infinity, of course. And then we have this x to the 2n power dx. X and 2n, they make 2n plus 1, and then we're going to switch the order. You can use dominant convergence theorem, because we're on an interval going from 0 to 1, and then the 1 over 1 minus x is from negative 1 to positive 1, so technically we are in the radius of convergence, meaning we can switch those two symbols. Alright, so that was a lot of talking for one step. So we have this equals to the sum. N equals to 0 to infinity. Okay, and then we have this x to the 2n plus 1 times the natural log of x dx right here. And if you notice, we have a generalization integral later. I should have put this integral before that because we have something like that here. But you know what? We're going to use integration by parts like everyone else does. So use integration by parts. di plus minus differentiating natural log. We get 1 over x, and then integrating this x to the 2n plus 1, we get x to the 2n plus 2 over 2n plus 2. Alright, so, sum of, let's see here. We have this x to the 2n plus 2, natural log of x over 2n plus 2. We go from 0 to 1, and then we are going to subtract the integral going from 0 to 1, and then we have this 1 over x times this x to the 2n plus 2, great, 2n plus 2 over 2n plus 2 dx. Now, if you plug in 1, we get 1 times 0, which is 0. Subtract, plug in 0, and we have a 0 times negative infinity situation here. But I might do a proof in this later. But, like later in another video. But for every single p is bigger than 0, or p is bigger than, no, it has to be strictly greater than 0, I think, x to the p times the natural log of x, as x goes to 0, will always be 0. So in this case, we can say that this is 0 minus this integral, which is just minus this integral. Okay, just this entire thing just becomes 0. Just go away. Yeah, this is negative times the infinite sum, of course, and then we're just move this 2n plus 2 out. We have 1 over 2n plus 2. We have this x to the 2n plus 1, we integrate that, and then plug in numbers. I'll just do everything in my head here, since we got a lot more to do. We got this crazy fraction. Alright, we get this is 1 over 2n plus 2. Right, and this is true because if you integrate that, we have x to the 2n plus 2 over 2n plus 2, and then we go from 0 to 1, plug in 0, we get 0, plug in 1, we just get this. So, next, how are we going to do this? Well, we just, we just do stuff, I guess. The sum n goes to 0 to infinity. Alright, this is 1 over 2n plus 2 all squared. This does seem like a satisfactory answer, but we can improve on this. Think back to how Euler originally did the series of 1 over n squared, which is pi squared over 6. We have something very similar to that, because if we factor out a 2 and then remove this 1 over 4, right? So this 2 is squared. We move this 1 over 4 out, we get negative 1 over 4. And all we're left with is the sum, n equals 0 to infinity, of 1 over n plus 1 all squared. Now, this might not seem like a very good thing, because we have this n plus 1. But we are going from n equals 0, and we are also ending at n equals to infinity. Meaning that if I increase the bounds by 1, I don't have to increase this top bit, because infinity plus 1 is still infinity. And next, this plus 1 will just disappear, because we bumped the numbers up by 1, so this goes down by 1. And as you can see, this is pi squared over 6. So at the end, we have negative pi squared over 4 times 6, 24. In the future, I might be doing these integrals in one video, like dedicated to these integrals. And hopefully in that video, I will do the proof that this is 0. Anyways, this one is done, and you guys can take a look. And I do apologize for the sunlight. It is a little bit blocking the view, but you know what? I don't care, because we got this integral that should have been before done before. I just thought this. And this is a long video. This is already something of a 23 minutes. Alright, we have this left. Okay, the integral going from 0 to t of x to the a times natural log of x. We're going to have to draw upon the limit again, because of course we have that 0. And this time I will show you why that is 0. If you plug in 0 to here, you will get 0. The integral from 0 to t of the x to the a times the natural log of x dx. And then, of course, we're going to start with a simple... Actually, wait, I did not erase this integration by parts, so... Okay. I don't want to... Alright, so di plus minus. You can also use the u dv, but I prefer the di. Anyways, we're going to differentiate natural log of x like before. We get 1 over x, integrating x to the a, we get x to the a plus 1 over a plus 1. And next, what we're going to do, we're going to have to just draw upon the usual stuff. So, yeah, this equals to the, no, it's not the integral going from 0 to t anymore. This is going to be x to the a plus 1 times the natural log of x divided by a plus 1. And then, of course, this entire thing is going from 0 to t, and then you're going to subtract it, and going from 0 to t of 1 over x times x to the a plus 1 over a plus 1. Let's do this limit in our heads. And I'm sorry because I have no room left in this board. Alright. Move this a plus 1 down into the denominator. You get a negative power. And then this is negative infinity. That's the natural log of x part. And then you divide by infinity. That's the x to the negative power part. And we are assuming that a is a positive number. I am not sure if this is correct, if a is a negative number, so anyway. You do L'Hopital's rule. 1 over x over this. Negative 1 is negative times this a plus 1. And then we have x to the a plus 1, and then you subtract 1, right? That's the power rule for derivatives. And then you move that constant out, and then you move that x down, x at the top down. And then you notice that this is 1 over x to the negative power. That's x to the positive power. And then, when x goes to 0, that goes also to 0. And so this entire thing is 0. Plug in t. That's all we gotta do. We have this equals to t to the a plus 1 times the natural log of t over a plus 1 minus, this is going to be 1 over a plus 1 times, this is going to be integrated, x to the a. We get x to the a plus 1 over a plus 1 again, going from 0 to t. Plugging in 0, we just get 0. Plugging in t, we get something like that. That's something weird, I should say. So you have t to the a plus 1 times the natural log of t over a plus 1 minus 1 over a plus 1. We have, this is t to the a plus 1 over a plus 1. And next, you can also factor out a 1 over t to the a plus 1 over a plus 1. I'm going to do exactly just that. And here we get t to the a plus 1 over a plus 1 times, everything is factored out in this except the natural log of t. And then over here, we just got to subtract 1 over a plus 1 right here. Hopefully this is correct. This seems all good to me. This seems very good to me. Okay. What is next up on the menu? We have the biggest partial fraction you will ever see in your life. Probably not. You could probably do more, but my life, God, the integral. This is not the antiderivatives. We're not doing the definite integrals before. We're doing the indefinite integrals now, which is not great at all. 1 over x plus 1, x plus 2, x plus 3, x plus 4, x plus 5. All integrated with respect to x. This is a very big one. We're going to do a massive partial fraction. And I don't want to, but this is the only way. So 1 over, this is going to be x plus 1 times x plus 2 times all the way up to x plus 5 is equal to, let this be sum a over x plus 1, and then you're going to add sum b over x plus 2, and then you're going to add some c over x plus 3, and then you're going to add some d over x plus 4, and then you're going to add a capital E, not the irrational number e, x plus 5. Alright. You can use the plug-in method, or how do you call it? Just cover-up method, the plug-in method, something like that. I'm not really sure what the name of that is, but we can use that method to cover up the x plus 1, and then you want this x plus 1 to equal 0. That means x equals negative 1. And then you plug in, that's why this is called the plug-in method, to everything else. Okay. You can do the calculations, but I think I know what it is. So, plug in negative 1 here, we get positive 1. That makes no use at all. Plug in negative 1 to here, we get 2, and then we get 3, and then 4, so we get 4 factorial, which is, I think 1 over 24. I think here. These are all positive, right? So, yes. Yeah, they are 1 over 24. Next, let's try to find b. b. For this b part, we're going to cover up this, and then we're going to plug in negative 2 to every single other one. Over here, plug in negative 1, we just get a negative. Over here, we get a positive 1. That makes no use whatsoever. Plug in to x plus 4, we will get 2. Oh god. We get a 2, and then plug into x plus 5, we will get 3. We will get 3. And then negative 1 times 1 times 2 times 3 is negative 1 over 6. Is negative 6, but then you take the reciprocal, so negative 1 over 6 is our b. Next for the c, I'm going to speed up the pace of my speaking here. Plug in x plus 3 into right here, and then plug in all the other ones. Plug in negative 3 to here, we get negative 2. Plug in here, we get negative 1, so that 2 negatives cancel out. We just get a 2. And then plugging in this x plus 4, we get 1. That does absolutely nothing, so we still have 2. And then plug in this 5, we will get 2. I'm sorry if I spoke a little too fast here, but I am pretty sure we will get 4. We will get 4? Yes, we do get 1 over 4. We do get 1 over 4. C is 1 over 4. D. Find D. Alright. To make this 0, x has to be negative 4, and then you plug in negative 4 to everything else, we will get, this is going to be negative 3 to negative 2, so we get positive 6 times x plus 3, which is just negative 1. This becomes negative 6, and then you have to multiply by x plus 5. X plus 5 is positive 1. So we get this is going to be negative 1 over I have to double check here because I can't speak too early. Wait, hold on. So this is going to be positive 6. Plug in x plus 4 into x plus 3. We get negative 1. So we have, so these are, this x plus 1 times x plus 2, if you plug in negative 4 as a positive number, because this negative and negative cancel, we get 6, and then you multiply by this negative 1, and then you multiply by this positive, yeah, it is negative 1 over 6. Oh god, I haven't done this problem in a while. X plus 5, plug in x plus 5, we will get negative 4. Oh god, I just accidentally drew over my shirt here. X plus 4. That's this part. X plus 3. What am I talking about? Plug in negative 5 to here. We get negative 4. Negative 4 times negative 3 over here will result in a positive 12. Positive 12. Next, plugging in x plus 3, if you plug in for x, you get x plus 3 is negative, I want to say 2, negative 2. Yeah, negative 2. We get negative 24, and then you plug into x. Oh, so this is also positive 1 over 24. That's really interesting because A is equal to E, B is equal to D, and C equals equal to C, whatever. Anyways, oh goodness gracious. So we just plug in. So we have 1 over 24. We're going from, actually, no, we don't have any going froms. 1 over x plus 1 dx, and then you're going to subtract, because this is a negative, minus 1 over 6, the integral of 1 over x plus 2 dx, and then you're going to add 1 over 4, the integral of 1 over x plus 3 dx, and then you're going to subtract again, and then we have this 1 over 6, the integral of 1 over x plus 4 dx, and then you're going to have to add 1 over 24 times the integral of 1 over x plus 5. Now, the coefficient on x on all of these integrals is just 1, so we don't have to divide by anything. And here, we are allowed to use the natural log. And I might factor out these constants. Yeah, why not? We have this equals to natural log. We do need the absolute value of x plus 1. And then you have to add the natural log of absolute value of x plus 5. And then, so this way, you can divide by 24, since these coefficients are all 24. And then you're going to have to subtract. This is going to be this natural log absolute value of x plus 2 plus the natural log absolute value of x plus 4. And you divide by 6. And then you're going to add just this one lonely term, natural log absolute value of x plus 3 over 4. You can also use properties of logarithms and bring these together, but you know what? I'm gonna leave it as can be. And that is another solution. Alright, interesting. And the integrals are all done. Time for the series. And yeah, these series probably won't take too long, since we're just going to prove if they are divergent or convergent. And we have this extra fun thing, the sum of Riemann zeta. It's fun. Yeah, it's fun. Alright, the first one, the sum, n equals to 0 to infinity of inverse cosine of n over e to the nth power. I would probably start by using the test for divergence. Basically, we would take the limit as n approaches infinity, of inverse cosine of n over e to the n. Now, inverse cosine is a continuous function on its entire interval. So we can move this limit inside. We've got this equals to inverse cosine of the limit as n approaches infinity of n over e to the n, which is just 0 in this case because the exponential function goes much faster than the polynomial function. Yeah, the polynomial function. So we get this equals to the inverse cosine of 0. Now, the inverse cosine of 0 is pi over 2. So this is pi over 2. But the important thing is, this is not equal to 0. Meaning that this is divergent by the test UTFD. Test for divergence. And think back to the test for divergence. What does that even mean? Well, the sum means we're going to add up every single term. And if we're adding up infinite things, if the limit does not go to 0, meaning you add infinitely many positive things or negative things, and you will go divergent. Sooner or later, you will if it's not equal to 0. And that is why this is divergent. Okay, hope you guys have a chance to look at it for a while. We're gonna, oh god, I just, alright, the sum. N equals to 0 to infinity of sine of n over 1 plus 4 to the n. Now, take the absolute value. If I take the absolute value, you will notice that the absolute value of sine is always less than or equal to the 1, just 1. So, if I take the absolute value, this is going to be less than, that's a greater than, less than or equal to the sum, n goes to 0 to infinity of 1 over 1 plus 4 to the n. And of course, this is also smaller than by the property of fractions, n goes to 0 to infinity of 1 over 4 to the n. Right? Because 1 plus 4 to the n is always less than 4 to the n. So we can confidently say that this is less than or equal to. Next, this is actually, this is equal to the sum, and it goes to 0 to infinity of 1 over 4, all to the nth power. Now, look at this r. This r value, r is equal to 1 over 4. If I take the absolute value of r, this is less than 1, meaning that this is convergent. And this has to be strictly less than 1. Just note that. But this is less than 1 by a pretty good margin, so this is convergent. And meaning that the original sum is also convergent by, I don't know how you would call it, but this is going to be the direct comparison test. Of course, and that is the convergence. Okay. We have a big, interesting, sum coming up here. The sum of another sum. The sum. N equals to 2 to infinity of the sum. I'll use k. Why not? K equals to 1 to infinity of 1 over k to the nth power. Well, what can we do here? Should we switch the order of summation? Well, that might be a good idea. I mean, if we switch the order of summation, then the inside would just be a geometric series. However, we could just do this using a regular test for divergence. That is my favorite way of proving if a sum is convergent or not. We could just do this. The limit as n approaches infinity of the Riemann zeta function of n. Is the Riemann zeta function a continuous function? For the sake of this video, I'm going to say that it is, and that is convergent, continuous on its interval. So we have this goes to the Riemann zeta function of the limit as n approaches to infinity of n. Alright, well, we have the Riemann zeta function of infinity. Now, this is equal to the sum. N equals to 0 to infinity, and of course I have to change this variable because we already have an n. Let's see here. 1 over s to the limit as n approaches to infinity of n. Now, if as n goes to infinity, the first term will always stay the same. Wait, no, this is supposed to be a 1. the first term always stays the same, meaning that this is going to be 1 plus. Plug in 2, as limit as n goes to infinity, that goes to infinity, and then the reciprocal goes to 0. So technically, you're adding 1 plus a bunch of 0 pluses, which is not equal to 0. Meaning, since this is not equal to 0, meaning that this is also divergent by the test for divergence. Alright, well, that was an interesting sum, but, oh, God. It's alright. It's fun. It's alright. Yeah. Anyways, that wraps up this video on all the calculus problems, and I hope you guys enjoyed it. I certainly did. I certainly enjoyed talking for 45 minutes straight, so I'm gonna see you guys when I'm 11. Bye!